Hi everyone. In this presentation, I'm going to talk about the enablement of AMD SEV in Zen. So a little bit about me, because it's my first time presenting at Zen Summit. So I have been working in the kernel and related communities for about 8 years now. And this is my first job working in the Zen. And it's been fun so far. I work at Vates, and we have been sort of working in past few months as part of Open HyperX project to enable AMD SEV, SEV-ES, and SEV-SNP. So, little agenda for this talk. So first, I kind of wanted to go through AMD's memory encryption technologies. I know that there was a talk in 2016 when AMD came up with these technologies at Zen Summit. But after that, AMD has, of course, come up with ES, SNP, and also IO-related stuff. So I thought it would be a good idea to also kind of give an overview of a bunch of these technologies, especially the one which we are going to handle as part of the Open HyperX project. And then I sort of wanted to dive a bit more into how AMD SEV works and how the structure will look like roughly with respect to Zen, and a little bit of like the upstream status and where we are at and what we are planning to do. So that's mostly going to be agenda for today. So as I mentioned, in 2016, AMD announced their SME and SEV technologies as part of confidential computing. So you might have heard of confidential computing in general in one sentence. In one sentence, it means to encrypt your data while it's been in process. Before we have de-encrypt, where we are encrypting the whole disk, or even VPN. So it's not a new concept. But mostly here, it's about the data which is in process in the CPU. And this is basically being done by AMD's SEV technologies, or with Intel, there is TDX. So that's mostly related to the confidential computing. And AMD started providing these extensions around 2016, and it's mainly focused, so for example, the first one was SME, Secure Memory Encryption, which is mainly focused on the main memory encryption via dedicated AES engine on the on-die memory controllers. And here the encryption of the data is being done with the 128-bit encryption key. Now this key is basically used by AES engine with SME. A is basically randomly generated by the hardware on each system reset, and is entirely managed by something called AMD Secure Processor, which is a completely different chip, ARM Cortex A5. So it's kind of separated from the x86 part of the SVM. And SME basically provides the ability to set something called C-bit, which is basically a physical address 47. And the OS or the hypervisor needs to set this bit to mark the encryption of pages. So this can be basically manually set by the hypervisor that, okay, you want to mark this page or this page as encrypted one. And then it could be like automatically encrypted and decrypted while entering and going out of the AES engine in the memory controller. With respect to SME, there are basically two models to be able to use it. Either you do the full memory encryption, and when you do this, basically it could be useful for like, I don't know, like the government centers. So where you need full memory encryption to encrypt all the DRAM content, which can provide the strong protection. And the second way you could use it is the partial memory encryption, which could be useful for, like, for example, for the guest VMs. If you want to encrypt the data which is belonging to the certain chunk of the certain set of the pages. And this basically can be handled by OS or hypervisor. So while SME as a technology provides a lot of flexibility, it does require support in OS and hypervisor. So if somebody doesn't want that, there is also an option called transparent SME, which is basically just provided in the BIOS, and it kind of encrypts everything for you. It provides all the physical protection that's needed. So you don't really need to mark the C bits associated with specific pages. And SME is basically, SME and SEV both is available from the first generation of Epic lines. So that was mostly an overview of SME. In case anybody is interested in with respect to playing around it, we had a little bit of demo prepared last year, so you can check out the link. And along with the SME, SEV, AMD came up with the SEV, which is basically using the SME in conjunction with the AMD V technology. And the goal is basically to provide the protection from a various sort of cross-VM and hypervisor-based attacks. So SEV is kind of built around the idea of the secure sandbox environment, where software can execute and is protected from all of the software running on the system. So it could be used for the full big VM, or it could also be used for the containers. So there's also like the projects like confidential containers where it's already being used. In SEV, mainly the encryption key is using a hardware tag called ASID. Now this ASID is basically part of the AMD SVM, the virtual machine control block. I'll go a little bit deeper into it later. But the idea is that the tag is basically kept with the data all the times when inside the SoC. And that prevents data from being used by anyone else than the owner, which is like the guest. And AES with the 128-bit encryption protection data outside the SoC. So when data leaves or enters the SoC, it's accordingly encrypted and decrypted. So also in the case of SEV, each VM, of course, has their own single key, which is associated with its own ASID. But also, there's a different key for the hypervisor. I'll talk a bit about it, why and where it could be used. And SEV uses the same encryption engine as SME and CBIT to mark the encrypted pages. But there are certain restrictions with respect to which pages could be private and shared. The choice is being done using the standard CPU page tables. And as I mentioned, the private pages can be, of course, marked with the guest encryption key. And shared pages can be marked with the hypervisor key, or it cannot be encrypted at all. That's upon guest. So so as I mentioned, there are some restrictions on the data in the shared pages. But for example, the instruction pages always have to be private. So that was kind of an overview of SEV. After SEV, in 2017, 2018, AMD announced SEV-ES, which is sort of like a one further step from SEV. And this is to prevent or to protect the guest VM from the attacks on its register state from the malicious hypervisor. These attacks kind of may include reading the guest register values, writing malicious values, or even sort of replaying the old state back. Reading the guest register values from malicious hypervisor can, for example, result in silent data exfiltration, for instance, by reading the XMM registers, which are like typically used to hold the AES keys. using the x86 AES instructions. So SEV-ES basically encrypts and integrity checks the guest VM's register state against this sort of attacks. It enables the guest VM to decide what information at which state it wants to share with the hypervisor, so it's sort of per case basis. Although there are, of course, situations when hypervisor needs to access VM registers for things like device emulation or MSR handling. And in such case, it's upon guest VM to explicitly decide which register state it chooses to share with the hypervisor. So it's kind of similar with SEV, but in SEV, you decide and encrypt the specific pages, and here you go one step further. And this is kind of actively done using something called guest hypervisor communication block, which is being introduced as part of this technology. So just to give a little bit of idea, initial register state is encrypted and measured as part of the SEV guest launch. Then every time VM run happens, integrity check is performed on the saved state. So the legacy AMD V architecture kind of changes here, because now all the register states are kind of saved at the same time. So your VM CBE is also expanded, and then you also have like a control area and save area, and control area is basically pointing to the save area. And then save area is basically expanded to save all the register values at the same time. So that's kind of a gist of SEV-ES. For those who are interested more in it, there's a white paper on it. And then after SEV-ES, AMD came up with SEV-SNP. The goal of it is to basically prevent software-based integrity attacks and reduce the risk associated with the compromised memory integrity. The basic principle of SEV-SNP integrity is that if a VM is able to read the private encrypted page of the memory, it should be able to read the last written state of it. And SEV-SNP focuses on the integrity attacks like the replay protection, data corruption, remapping, etc. And for attacks like remapping and for the attacks like replay protection and the data corruption, attackers usually rely on untrusted code being played. So this is basically addressed by again introducing another block called reverse map table. The goal of reverse map table is basically simple. It tracks the owner of each page that's being encrypted. And these pages of memory can be owned by the hypervisor, guest VM, even AMD SP, the secure processor. The RMP is used in conjunction with the standard x86 page tables to enforce the memory restrictions and page access rights. SEV-SNP also introduces a new optional feature called virtual machine privilege levels. This sort of allows guests to divide its address space into 4 levels. And then you have like the level 0, which is like more, which gives you more accessibility rights. And general goal is to like provide the isolation abstraction layers. This is also kind of used this is one of the important things for also live migration and related technologies. I won't go much into detail of it, but yeah, we can talk about it later. So just a little trivia that SEV-SNP is basically available from the 3rd generation of EPIC, and SEV and SEV-ES is from 1st and 2nd generation. Also, I think from the 1st generation and between 1st and 2nd generation, with 2nd generation you have like much more amount of ASID keys available. Um, and as part of the Open HyperX project, we plan to enable all three of them. So you can look at the plan I had sent in upstream just to get an idea of what kind of phases are involved. So this is basically how the high-level AMD SEV architecture would look like. So main job of the hypervisor here is to communicate with the AMD Secure processor. And this is mainly with regards to key management. As the security of SEV is kind of highly dependent on the security of these encryption keys, like I mentioned, the secure processor is completely separated. And secure processor's firmware kind of provides commands and APIs using which the driver in the hypervisor can communicate with regards to a bunch of different things. So like I mentioned, each encrypted page is associated with the tag ASID, which is part of the VMCB. And this CPU ID lifts can be used to determine what's the minimum supported keys and what's the maximum supported keys for each platform. So with regards to restrictions about private and shared pages, so one of the things is that instruction code pages and guest page tables always have to be private under SEV. It's part of their technology. And then data pages is something that can be decided by guest. And shared pages are mostly being used to communicate with other VMs and hypervisor, of course. And yeah, last but not least, all DMA must occur on the shared pages. So
one very quick thing, AMD Generation 5, which was announced earlier this week, has a new technology called SEV-enabled, which addresses the DMA to encrypted pages. So
right.
That's brand new this week, if you want to read about it.
Yeah, okay, thanks. Yes, so if we zoom in a little bit from the previous diagram, first thing, of course, we need in Zen is this ASP driver, which can talk to the AMD SP. So the main job of it is the programming and management of encryption keys and secure data transfer between guest VM and hypervisor, as well as the as well as the transfer of the keys with AMD Secure processor. So there are mainly two jobs of AMD Secure processor driver. First one is the platform management cycle. So there are a bunch of APIs provided by the firmware to which basically includes the init, shutdown, status, and reset. And then you sort of also have a bunch of keys associated with it. So it sort of also does the whole root of trust with regards to the key exchange, and also to make sure that the keys were generated on the same platform. So there are a bunch of those things which also ASP driver need to be able to call. And then you sort of have the second set of the commands, which are related to guest management lifecycle. So these basically include all the commands related to launching, running, snapshotting, migrating, and decommissioning the guests. There are also debugging related APIs to help the developers, which is nice when the guest crashes. And one of the good thing about AMD, and shout out to AMD for also open sourcing their firmware for AMD SP. So that's definitely nice to be able to look into it. I think they open sourced it like a year ago or so. So it's there on the GitHub. It's just the open source. It's not the open source development process that's happening over there, but it's still nice. And once we have ASP driver here, we will need the SVM operations to do a bunch of things. So one of the things, of course, the SVM operations need to do is to kind of provide the guest management related nicer interface to be able to talk with the low-level libraries like libxl and stuff like that. And another thing which we need to handle is with regards to the ASID management. So one of the things that comes with the SEV is that now you have minimum ASID as well, which is something we don't have right now in Zen. And it's a must that you have to kind of manage the different ASID spaces for SEV, SEV-ES, and SEV-SNP guests. Because I think it's also a security issue if a guest is started as SEV-SNP and then is changed to SEV, SEV-ES. So it's sort of recommended that you have the different ASID blocks for non-SEV guests, SEV-ES, and SEV-SNP guests. So that's also one of the things which we need to handle. And also with SEV, the thing that changes is you sort of need a fixed ASID for each VM for all the vCPUs that are related to the same VM. And this ASID needs to be fixed all throughout the life cycle of the guest. So that is also something that needs to be fixed in Zen, because right now they are constantly changing. I'll have a design session tomorrow, I think, to talk a bit more about it for anybody who's interested in it. And then once we have like this SVM operations, we need to also change a bunch of things in libxl. Of course, the first thing would be to be able to create the secure guest. One of the other things is that as part of the SEV guest launch, we also have the SEV guest launch finish, which for non-SEV guests we don't have. So those APIs also need to be put together into libxl, and for libxl to be unable to handle them. And I think also, of course, the create guest hypercode will need to be changed a little bit to handle that. And then I think on the high level, we will have an option in Excel for the user to be able to provide that, okay, they want to start the guest, which is the SEV guest. So, I mean, once we have all the dancing done in the libxl, I think for Excel it wouldn't be much. But of course, people who are more familiar with the code can chime in. So that's basically how the development would look like for it. Of course, this can change with respect to nitty-gritty details once we send the upstream stuff. But yeah. So a little bit of upstream status, which I wanted to mention. So we have bunch of parallel work going on. So first, I think, is the implementation of the AMD Secure Processor driver from my colleague. And also as part of that work, something that came up is to kind of do the infrastructure improvements of AMD SEV and VM lists, which Andrew wanted to do. So there's a work going on with regards to that. And then parallelly, we have been toying with the idea of introducing the Zen-wide ASID allocator to have the fixed ASID not only for the SEV VMs, but also for non-SEV VMs. So yeah, feel free to check them out. And yeah, that's mostly my talk. That's the upstream status. And yeah, thanks to Andrew for being available for all the questions for us. Yeah.
What about attestation?
Sorry?
Attestation. If I would like to check that the VM was actually secure, if I have already the attestation process running on top of a KVM, would I be able to read
KVM?
If I have
Yeah.
implemented somewhere already,
Okay.
can I get the information about a VM running on top of Xen and be sure that it's actually running secure? How to make sure that this is actually running secure?
Yeah. I mean, so AMD SP as a firmware provides a bunch of API to you to be able to do it in your particular scenario. We'll need to check what details and what kind of attestation you require. But as a firmware and the APIs provided by AMD itself, there's already some attestation with respect to platform going on there. So that is something which Zen will already do as part of ASP drivers. So yeah.
It's probably worth saying that the reason a lot of this is very invasive in the domain creation is because every single thing you do to the guest needs negotiation with the PSP so it can measure it. And one of the things that you get is the create complete.
Yes.
Is an API call to the PSP, and at that point you can ask the PSP for a quote of it. And that is per the AMD specification, so it will be exactly the same as what KVM would produce, what all the other hypervisors would do, because it's spec by AMD. It's not specific to the hypervisor. So yes, we get that, and then whatever other attestation service that's going on, I know there are a lot of fights as to how that attestation gets done. But
today it looks pretty simple. There's a public key. You get the information from the hypervisor and you verify that the signature is correct, and then you trust everything. So that's the same.
yeah, but it's the trust everything that people are arguing over. But yeah, the quote about the state of the VM comes from the AMD PSP, and it's the same. It's the same for any hardware vendor that has. Sorry, it's the same for any hypervisor vendor that has implemented this technology.
That's what I wanted to hear. Thank you.
Yeah, because it's the firmware API, so you have to talk with it. Yeah. Any other questions? No, not necessarily. I mean, I think for the HVM also it could work. Well, for the DOM 0, we don't have HVM DOM 0, so yeah. I think for PV, I'm not sure. Well, for PV, you don't have the...
Basically made a demo for SME based on DOM 0 PDH because we had to have P2M to encrypt pages between DOM 0 and okay. So this is just was required for the demo. Normally we don't have to have DOM 0 PDH.
Okay, so you can map pages from an encrypted guest on a PV.
Yeah, so because PV guests share page tables with the hypervisor, they're all in ASID 0. So from AMD's architecture point of view, all PV guests completely are hypervisor context. They're strictly in ASID 0. They can do anything that hypervisor context can do.
Is that a problem when you also have other untrusted PV guests in that mix? They share the same ASIC?
Don't do that then.
On the other hand, the SEV guests are protected against the hypervisor, so they are protected against the PV guests.
But if you allow them 0 to map a page, then you also allow another guest to map a page.
Well,
That's the hypervisor to handle, right?
and you can also only one of the big things with SMP is there's a pair of instructions that are only used by the hypervisor and a pair of instructions that are only used by the guest that do a two-way handshake negotiating the state of every page. So the hypervisor can only map a page that a guest kernel has explicitly said, yes, this is a shared page. You can map it.
Yeah, it's not allowed, but you can't. The guest can detect this.
Yeah, you can map it and you can try and read and write to it with page fault.
Yeah, but I mean, since all
in the hypervisor, they don't let you do that.
But we've got the standard
Yeah.
page table protections that we normally use to keep one PV guest out of another, and that's still, the thing is, we Zen trust ourselves, it's only the guest kernel that doesn't trust us in this scenario.
Okay, I think I'm out of time, so thank you.